Hello everyone and welcome back. In this lecture, we want to talk about E MOSFETs. And this is maybe the most important field effect transistor in existence. So this is the one you really want to make sure you understand because there are some pretty key differences between N and P channel. And I'm going to try to simulate a couple of circuits so you can see what those differences are, because these are really the building block behind many different devices. There are definitely applications for JFETs and depletion MOSFETs, but the enhancement MOSFET is really where these things shine. So the enhancement MOSFET in some ways is similar to a field effect transistor trying to behave like a binary junction transistor. So to do a quick review, if you remember from the BJTs, this would be an NPN, and this is going to be normally off until we have current flowing between the base and the emitter. And the PNP is the same way. We need that current flow between emitter and base in order to activate the larger current flow. So an enhancement mode MOSFET has an insulated gate, so we will start by drawing that. So we have our gate, which is insulated. And then there is something kind of different about them. So the first thing that is a little bit different is the gate, in this case, is actually up against the substrate. So you'll remember from the D MOSFET, there's a gate, there's the source and drain channels, and then there is a substrate that sort of surrounds them. In this case, the substrate goes like this. So this would be our P substrate, and this is for an N-channel MOSFET. And we have our N channels on the top and bottom. So we have the drain, which would go to positive, and we would have the source, which as usual goes to negative. So in an N channel, the source is always negative, remember, and in a P channel, the source is always positive. So that is, kind of standard. What's different is the gate. So the first thing to understand in an E MOSFET is it's going to be normally off. Like unlike a JFET or a depletion mode MOSFET, there won't be a normal, I'm trying to say this carefully because this is not totally correct, but basically, the gate isn't in an N channel existing to stop the flow of electricity. In an N channel, positive voltage to the gate causes conductivity. So what happens is when we apply the positive voltage, we pretty much open up a channel to allow this to start conducting. And because it's going through a P substrate, the major carrier in this case is actually a hole. A P channel, on the other hand, is going to actually be normally on. So I'll draw a diagram of this. So in the P channel, we have the gate. There's our N substrate, and then the P drain, P source. This needs to connect to positive, this needs to connect to negative. And in this case, when we apply a positive voltage, that causes conductivity to stop. So it basically creates a depletion field and shuts it off. So the P channel is normally on, so it will conduct like normal through the source, the substrate, and the drain. So that is one kind of sort of key difference between this. The gate in an N channel opens things up, and the gate in a P channel shuts things down. So let me show you a quick simulation of both of these, and you'll hopefully understand. So the first thing I'm going to do is I'm going to grab my active components in Falstad. So I want an N-channel MOSFET, and you can see this is the symbol. The gate here, the source points at the gate. So this kind of U-looking shape is always the source that goes into the gate, and then the drain at the top. I will also go ahead and draw a P-channel MOSFET down here. And again, the source is the U part of this. So and this time it's pointing away from the gate, and that's the P channel, which is a little bit the opposite of binary junction transistors, but you just kind of get used to this with practice. So remember, if we set up our circuit, I'll go ahead and add some voltages. So I'm just pressing V, and in an N channel, we want the source to connect to negative, the drain to connect to positive. And I'm going to go ahead and I'm going to press L to add in an LED light. And just to be safe, I'm also going to go ahead, I'm going to actually delete that. I'll drag it and then delete it, and I'm going to press R so I can go ahead and actually put a resistor in. And for now, I'm going to leave it at 1,000 ohms. And let me actually drag this down here. So that is that part of the circuit. And then we also need another voltage source that connects back to the gate. And I'm going to press S to give myself a switch. I'll open it up. And because everything needs to have a common, the negative of this will connect to the negative of that. And if I've done this correctly, and I believe I have, when I close the switch, you can see that it causes the electrons to flow. So one thing to be aware of is because of the high impedance here, you have almost no electron flow in the circuit containing the gate. So this junction has almost no flow, which is one of the major advantages of MOSFETs, that insulation causes the electron flow to be so small that it's practically no energy being used to energize the gate. So in this case, when I apply this positive voltage to the gate, it causes the circuit to energize, and when I take it away, the circuit de-energizes. And we're going to contrast this with the P-channel MOSFET down here. Again, my source is at the top, the drain is at the bottom. So in a lot of ways, it's going to look like a similar circuit because the source has to go to positive in P-channel. So the MOSFET is flipped, not the battery. Whoops, wrong. So I'll draw a wire going up. I just press W to add in a wire. L for another LED. And connect that down. And I'll go down from the drain. R for a resistor. And I will connect that. And you'll see already this thing has started conducting without anything else on it. And that's the big difference. This requires an applied voltage to turn it on. This, the P channel will just be on. It'll create this bridge through the gate naturally when there's a lower voltage at the gate than at the source. And that's how this is all determined. Here, if the gate voltage is higher than source voltage, it creates, it closes this connection and causes current to conduct. Here, if the gate is less than the source, it conducts. Here, the gate has to be more than the source. So if I go ahead and add in another voltage, like so, and I'll add in a switch like so, you'll see that immediately this thing has been locked out by the voltage applied to the gate. So when I take the voltage away, it conducts. And I can actually reduce this to just 500 ohms so it conducts a little faster. And I'll do the same thing. I'll actually make this one 200. So there we go. And there we go. So that is the significant difference between N-channel and P-channel enhancement MOSFETs. They're extremely useful. We're going to talk about them later. And a lot of times when people talk about MOSFETs, they're specifically talking about these. The depletion mode MOSFETs do have their place, but they're a little bit less common. These are really the default ones people are referring to. So if you understand that the gate is insulated and how you're applying positive voltage to the gate in both cases, but it's going to have an opposite effect, you will be in good shape. So there you go. That is what you need to know to get started with MOSFETs.